Hello, everybody. Welcome. Welcome to the 69th Conference on World Affairs. We made it. Yay-ho. It's so good to be here with all of you for what I know is going to be the best CWA ever. I'm Betsy Hand, Community Chair of the 2017 Conference on World Affairs, and for the past 7 months, I've been one of 2 cheerleaders for an awesome group of volunteers who have recruited incredible speakers and performers who will come to Boulder from around the country and from 18 countries. They've come to surprise us, to entertain us, and most importantly, to challenge us to see new things in new ways. And I thank you, CWA speakers who are all here. Thank you. CWA exemplifies what a true town-gown enterprise can be. It's a wonderful partnership of community volunteers with the University of Colorado. Thank you, Chancellor Stefano, who you'll see in a minute, for your support. Thank you, program committee members, and you're all here too. Thank you. And I want to thank especially the CU students who play a key role in creating and producing the conference. Thank you, CU Student Squad, and your amazing leaders, Tess Rose and Alex Atwater. Thank you, Tess and Alex. You guys are fabulous. We're so grateful. Now I'd like to acknowledge the office team who took the program and made it happen today and the next 4 days. Alan Culpepper, Katie Grady, Aaron Rain, and the CWA Faculty Director, John Griffin. Thank you. Yay. This has been a great partnership, and I'm proud to introduce my co-cheerleader for this conference, John Griffin. Thank you.
Don't go anywhere. Good morning, everyone, and thanks for the kind introduction, Betsy, and congratulations to you on an incredible program that your committee put together. I really want to pause for a moment to really acknowledge the incredible dedication of Betsy this year. In many nonprofit organizations or entities that are similar to ours, the role of community chair may be largely honorific. What Betsy does is incredible, from recruiting speakers to designing the program, creative arts endeavors, helping us to raise resources on behalf of the conference. So I really want to make sure that we give her a very warm round of applause. So what Betsy just described to you is basically where the CWA comes from. 700 volunteers, a conference staff, a faculty, students, and all the inputs into the process. I'd like to just spend my brief moment with you talking about something that the CWA tries to accomplish. And that is nothing less than to contribute to the search for truth through conversation. As I was doing my research on truth, I learned that the Oxford Dictionary word of the year for 2016 was post-truth. All of this talk about post-truth has left many people wondering, well, who could be against truth? When perhaps they should have been asking, is my way to get at the truth the only way or the best way? There are many paths to truth, introspection, writing, experimentation among them. I want to focus our attention briefly on one, I think, underappreciated path to truth, and that is conversation. The CWA embraces the notion that human conversations can shed light on what is true. As film critic and longtime CWA attendee Roger Ebert wrote about the Conference on World Affairs, how refreshing to witness intelligent people actually in spontaneous conversation. It is unusual to listen to people in the act of having new ideas occur to them. So, I hope you enjoy and learn from our CWA conversations that you're watching and participating in, and I encourage you to converse with each other this week, before and after panels, over lunch, and into the evening, in your search for what is true to you. Next, and quickly, before I introduce our next speaker, I want to highlight our fundraising motto for this year, which is Help CWA Thrive. We rely on your support to put on this great event every year. So please consider giving what you can to the Conference on World Affairs. And finally, it's my great pleasure to introduce CU Boulder Chancellor Philip P. DeStefano, a man who has devoted his life and career to the University of Colorado Boulder. Dr. DeStefano began his service to the university 43 years ago. He's been a member of the CU Boulder faculty since 1974, has been an assistant professor of education, rose to dean of the School of Education, vice chancellor, and provost before accepting his current role in 2009. Please join me in welcoming a champion of the CWA, Philip P. DeStefano.
Thank you, John, and welcome to a one-of-a-kind, week-long festival of ideas featuring thought leaders from around the world and every field of endeavor. Thank you for joining us for this exciting week. And I want to thank John and Betsy, the entire staff of the Conference on World Affairs, and more than 100 student volunteers who make this event possible. I also want to acknowledge a few people in the audience, starting with my wife, Yvonne, who's with us. Thank you for being here, Yvonne. Also, two members of our Board of Regents representing Congressional District, 2nd Congressional District, Linda Shoemaker. Linda, thank you for being here. And Regent at Large, Heidi Ganal. Heidi, thank you for being here. I also want to further acknowledge our long-standing collaboration with the Boulder community, whose partnership has made this conference a success for 69 years. 100 invited speakers take part in 200 panel discussions and performances that attract an audience of 70,000 to the campus. And it's great to see so many community visitors and alumni on campus who come from far and wide to enjoy the conference. And this conference is also a tremendous opportunity for our students. The Conference on World Affairs is a great manifestation of our 3 campus imperatives: develop tomorrow's leaders, be the top university for innovation, and positively impact humanity. The Conference on World Affairs helps us develop tomorrow's leaders by pairing each of our speakers with a student ambassador studying in the speaker's field of expertise. Our hope is that these ambassadors, if you will offer significant professional mentoring opportunities for our students that will continue for years to come. Since 1948, the Conference on World Affairs has been relevant to our times, the community, and the university. Our vision at CU Boulder is to be a leader in addressing the humanitarian, social, and technological challenges of the 21st century and this conference certainly personifies this. Now I have the great pleasure of introducing our conference keynote speaker, Dava Newman, who until January 20th was NASA's Deputy Administrator. As Deputy Administrator, Dr. Newman was responsible for providing overall leadership, planning, and policy direction for NASA. She is a professor of aeronautics and astronautics and engineering systems at the Massachusetts Institute of Technology. Her research includes advanced spacesuit design, dynamics, and control of astronaut motion and engineering systems design. She also is engaged in assistive technologies to augment human locomotion on Earth. Dr. Newman is no stranger to campus, and she's been a great friend to CU Boulder. She was on campus at this time last year, advising our students at our annual Aerospace Student Projects Symposium, in which student teams presented projects ranging from a 3D printed rocket propellant to search and rescue drones. We have greatly appreciated Dr. Newman's support at CU Boulder, and it's great to have her back. Her talk today is entitled Humanity's Exploration from Earth to Mars and Beyond. Please help me welcome Dava Newman.
Thank you.
Thanks for being
Thanks
here.
so much. Hello, everyone. Thank you. Thank you, Chancellor DeStefano, Betsy, and John. What an incredible conference, a unique conference. So it is just my distinct pleasure to be with you and take you on a journey, if I may. So I think there are some students in the crowd, so can you raise your hand if you're 26 years or younger? All right, thank you. Well, our Hubble Space Telescope has been discovering the solar system and our beginnings, the enduring questions. Are we alone? Are there other habitable planets? And is there life? For 26 years, your entire life, we've been searching. That's really what we do in exploration. And this is a great, great 3D view of Hubble. My favorite story about Hubble is we looked at a very dark spot in the sky. Very dark. If you put up your thumb, just as big as your thumbnail, it's pitch black. Do you know what we found in that dark spot in the solar system? 10,000 new galaxies. 10,000 new galaxies. So that just gives you the purview of what we're looking for and discovering these days. So I'll take you on a bit of a journey through the solar system. We've recently been to Pluto, the 9th. Dwarf planets count. I was kind of a dwarf basketball player in college, so I count dwarfs. And Pluto has a heart, as you can see. But we had never seen Pluto. We hadn't been close to it. We didn't know what it looked like until this mission in 2014 to get close and zoom in. And now we can actually see what it's made out of and the mountains and the chemical constituents. Why? Because, again, we're asking those questions. Where do we come from? What are the origins? And is there life? Continue our missions. There's an ion-propelled mission right now. Did you see The Martian? Hopefully people saw The Martian. Well, that was ion propulsion, and we are using it today on our Dawn spacecraft. And it's currently right now at the Dwarf Planet Ceres. Ceres had these twinkling eyes. It was looking at us. We didn't know what those were. So again, getting closer, we discovered Ahuna Mons. It's 5 kilometers tall, 20 kilometers wide. And what's twinkling at you there is sodium carbonates, one of the really important characteristic chemical signatures for potentiality of life. So in all of our exploring throughout, again, we're learning every day, every day. We've been to Jupiter most recently. We're in orbit at Jupiter today. Our Juno mission, it's the goddess of Jupiter. And it's in a very hairy, if you will, polar orbit around Jupiter for 52 days. The radiation environment on Jupiter is 20 million times more than here on Earth. So we kind of zoom in on polar orbit and we zoom right back out. We hope our electronics and our instruments make it. So far, so good. And we're inviting the world to join us in all of this exploration. OSIRIS-REx, we do have an asteroid mission. It launched last September. It's a 7-year mission. Forgot to mention that the Juno mission, 9 years. So all of this exploring is not for the faint of heart in space science, because all of our missions typically take a decade, and people spend multiple decades of their careers, just to get this data. OSIRIS-REx is going out to an asteroid, Bennu, to sample it and bring it home. It'll be the first asteroid sample return mission in history. It's in good shape right now. Continuing on, as a talk, because I'm passionate about Mars. I've spent my career thinking about Mars. How are we going to get people there in the future? But I want to show you a short video because we've been exploring Mars for the last 50 years, just a little bit younger than this entire conference. So the last 50 years, this is the progress that we've made and the successes on Mars.
Led by the extraordinary men and women of NASA and our Jet Propulsion Laboratory. Right now, the wheels of curiosity have begun to blaze the trail for human footprints on Mars.
I just want to call and say congratulations to the entire Mars Science Laboratory team and really all of JPL. You guys should be remarkably proud.
So that's what I spend my time doing, thinking about how we can get humans to Mars. Thank you. It's very inspiring. There is a plan. It's in 3 phases, as I like to describe it. Let's go back to Mercury, Gemini, and Apollo. I'm probably here today inspired by getting to the moon in the Apollo program. It was really instrumental in teaching me as a young girl growing up in Montana that all dreams are possible. If we clearly make it to the moon, then what's the next goal for humanity? And we clearly think for humans, the horizon goal is to Mars. Now, I'd like to tell you how we're going to get there. Starts in low Earth orbit on the International Space Station, where we currently are. It's phase 1. Phase 2, we move out to Earth-Moon orbit. That starts very quickly. 2018 is the first launch. I'll talk to you about that. And then in the 2030s, onward to Mars. But it really is low Earth orbit, getting back to the moon, and then onward to Mars. Because Mars is really hard, and it's really far away. But let me show you some of the data that we're currently getting from Mars. It's quite phenomenal. Again, searching for life. Earth and Mars are both 4.5 billion years old, sister planets. 3.5 billion years ago, we think Mars was warm, could have had life. Today, it's not the case. What happened? Well, if Mars was habitable, then what happened? What does it tell us? It tells us mostly about what I call spaceship Earth, life here on Earth. That's why we're so keenly interested in the past, in our sister planet. What you're seeing here is the evidence for seasonal water on Mars. We knew Mars had ice on the polar caps, South and North Pole, but now we actually have evidence for some water. Now, It's high in salinity, it has percolates. Don't drink it, not enough for humans, but it's really a phenomenal scientific breakthrough that now we see seasonal changes and some liquid. Also, love to show you this, this video. There's just background movement. I'm gonna show you this. Again, back to the story. Mars and Earth are 4.5 billion years old each. Why doesn't Mars have life today? Well, Mars has no magnetic global protective shield. Earth, we do, lucky for us. Without a global magnetic shield, we see the sun's solar wind and solar radiation literally ablating Mars' atmosphere away. So Mars today is left with 1% carbon dioxide atmosphere. And this is data from the MAVEN observer taking very recently. All these papers are just being read, but we can literally see the Martian atmosphere being ablated away. So it's fantastic new data, again, looking at our sister planet and looking at what's happened over history. So phase 1 of our journey to Mars starts on International Space Station, where we've had astronauts, continuous astronaut human habitation for the last 16 years. Is anyone 16 or under in the audience? Maybe? Not too many, but your entire lifetime, there's been astronauts living and working off the planet. We say off the Earth, but for the Earth. So let me tell you about some of our crews. You might know about Scott Kelly. He was up there for a one-year mission. He has an identical twin, Mark Kelly, who was on ground, former astronaut as well. So Scott performed over 400 different experiments, a lot of life science experiments. How do his muscles and bones, what happens to them? What about the radiation environment? And then what about the technologies that we can demonstrate? So we look at all the physiology, we look at how can we keep astronauts healthy and performing very well. Because this is just the one-year mission. They mentioned that the Mars mission is just under 4 years. About 6 months to get out there, about 600 days exploring Mars, and then about a year and a half to get home. So who's ready now for my 3.5 year mission to Mars? You might lose 30%, some of them are, I know some of the students are, and that's fine. You might lose 30% muscle atrophy, 1 to 2% bone mineral density per month. So we think about countermeasures, and we really have a pretty good handle on that. But again, going out to Mars, the radiation environment is something that humans have never been exposed to before, so we have to think about the countermeasures. So here's Scott and Shell Lundgren, a CU alum, MD. You can clap. There's Shell up in the top left. And they're eating lettuce. That makes me point again. The human factors, the mental well-being of the crew. When you get to eat a fresh salad and lettuce, it's huge. Show was up there for 6 months, right? Any fresh supplies. And they're sharing that with their international colleague, a Japanese astronaut. Really makes a big difference when you're working in very isolated, confined environments. So International Space Station is really critically important. 5 main international partners, the US, Russia, Japan, Canada, and then the European Space Agency, which is actually 22 nations. Those are the 5 main partners, but 95 nations have sent up experiments and done research, and so we're really all trying to work together. I think it's a great international model. So as an aerospace engineer, I'm a technologist, and I asked Scott, we only have till 2024 on space station to help you all get ready for, again, the moon and then Mars. What technology do we need to really study? And here was his answer to me. Oh, sorry about that. Here was his answer.
Ideal candidates for demonstrations for our future journey to Mars, as well as space suits. We need, I think, new spacesuit technology that requires less maintenance in space, and something that's going to be easier to work in on the surface under the Martian gravity.
So he said he might have known, that I was a spacesuit investigator, but he said life support systems and spacesuit. Again, we've been testing them out, but it's really critically important. We can only close the water loops and the air loops 65, 85%, right? That's not good enough. Again, off the Earth, but for the Earth, because we really have to have complete closed life support systems, and that'll be incredible. So our water filtering system, designed for space, is being used all over here on Earth. Critically important, clean water for the world. So we look at all these technologies really as dual use. It's really important to, I think about it in that manner. here's technologies, kind of my top picks, if you will. Again, we'll be on space station through 2024 with all of our partners, and some of the technologies that we're looking at, again, to take that next step, to go beyond. So I kind of look at our 16-year history all the way through 2024, now the next 8 years, as the experiment itself. This big, huge International Space Station in low Earth orbit. I look at it as the experiment itself. It's the first step to get us to Mars. Really important investment. This is the next step. So that's a... Thank you. So that's the next heavy lift launch vehicle. It will fly in 2018, called the Space Launch System. It needs a better name, so all students send in your names, because it needs a better name than SLS. And so we're well on the way. My prediction is that it'll fly in 2018 without astronauts on the second mission. It's being studied right now at NASA, but the second mission. So the entire decades of the 2020s, we have the heavy lift. That's what gets us to the moon and even beyond the moon into deep space. And this is more powerful than Saturn V. We haven't had this capability in the last 4 decades. So it's very exciting, and all my videos, it's really about the people. This is being built by over 1,000 companies throughout the US and every state, and very notably here in Colorado. Huge contributors to all of aerospace and all of our adventures. So it's really exciting. In the 2020s, we'll keep flying, hopefully once a year, again, to get back where humanity hasn't been since the 70s, into Earth-Moon orbit, buying down the technologies that we necessarily need for Mars. So here's what I call an infographic, and it's not just for you to read, but hopefully you can see some of the colors, because I showed you a Mars video of the last 50 years, but I only showed you the successes. Now I'm showing you the whole truth in advertising here. This is factual data. Color-coded from the Soviet Union, blue is the US and NASA. So we just tried to get to Mars first, and then we tried to fly by. Then we tried to stay in orbit. Landing is really tough. Only NASA, only the US has done that so far. So look at all those tries, but look at this last decade, actually the last 15 years. Look at all those green checks. Those are successful missions. And we say everyone's success is our success. We are really in this all together. And so the Indian Space Agency now has MOM, the Mars Observer, orbiting. And we have MAVEN, as I showed you data from NASA's MAVEN mission. And now the Europeans, the ExoMars, just got in orbit. So we can study the low, medium, and high atmosphere of Mars all the time, and then NASA has its rovers. Most notably, the Curiosity rover we get data from every day. So there's 7 world assets at Mars today. But again, so we're doing very well. We share data. Actually, the US and NASA gives the Deep Space Network as well as the navigational help. Next up, United Arab Emirates. They're going to have an orbiter mission in the early 2020s. Again, and we're all in. It's global exploration. We want everyone to succeed and all work together. So that's why I show you that, to really show you that it's for everyone. Anyone wants to participate in that 3 phases. US would like to lead and NASA, but it's really for everyone to participate in global exploration for the future. Now, these are the technologies that we need to work on. Just a picture of, I'll just highlight a few for you. In the video, you saw the capsule coming in hot. That's called entry, descent, and landing. Well, today, we've tried to land on Mars every which way. Airbags you saw, and cranes, but that was with 1 metric ton, the rover. A human mission, 10 to 20 metric tons. We don't know how to do that today. So we've teamed up, actually, as NASA and SpaceX and others, to try to say, can we do this entry, descent, landing? We need more data. This is what we have to test out. Once we land, it is a round-trip mission, so we have to ascend. Even harder yet, we have to learn how to live off the land. In situ resource utilization, ISRU. All successful exploration in humanity, you don't bring everything with you. You have to figure out how to live off the land. Well, let me tell you, Mars is really cold and kind of dead. We might find some fossils, right? So I challenge my engineers, the maker has to make you the maker. You have to make the maker out of basalt. Then it needs to make your parts. Again, you can't take all that mass with you. We need regenerative life support systems. So these are some of our big, big challenges. But again, we'll get there. And all the time, the precursor missions, the robotic missions will keep going. Mars 2020 you saw in the video. So first time we'll make oxygen on another planet. It'll take that carbon dioxide atmosphere of Mars, split off those carbon atoms, we'll be left with oxygen. Now, not enough for a human to breathe, but it's a first step. First time we'll make oxygen on another planet. So, how do we do it? If Mars is so hard, this is I think we call for everyone, it's global exploration. I think that critically, we have to continue, investing in science and technology. At NASA, I gave a word for failure. What? Right? On small things, because I think it's really important. How many people are, comfortable with failure? I sure am not. But we learn so much more from our failures than successes. So in the little things, the life cycle, so bringing in all good ideas and working together across the government, academia, and industry, and globally, as I said. So I outlaid an innovation framework at NASA that I'll discuss a little bit and show you some highlights in this next part of the talk. So innovation is all around us. So I'm going to divide it into continuous innovation. The same technologies, the same kind of business models, organization models, but doing things better. Every day, are we doing the best that we can? That's about 80% of innovation, it turns out. And disruptive. What about really changing the business model? For NASA, it was the organizational model, public-private partnerships. On the right side, what about revolutionary technology? That's the sweet spot for an engineer like me. What technology can we really change to be innovative, to do something new? Transformative innovation, I say do both at the same time. That's really tough. Transform the organization and the technology both together. So in a picture, it kind of looks like that, and it's actually benchmarked. A lot of continuous innovation, a lot of good things going on. I'd like to highlight some things. At the continuous innovation, things that you think, outreach, education. This is an example of a digital learning network to bring in all kids to say, is this exciting to you? Guess what? We want you to be part of this. Really bringing in folks, we need your ideas. Any age, we need ideas. How do we do things differently? Another example that I'll highlight is actually a conference, Mission STEM, science, technology, engineering, math, but talking to all universities on diversity and inclusion with a very, very important message saying that we need excellence. And the only way to get excellence that I know of is to be the most diverse and inclusive as we can. All I know is I can't work with a whole bunch of other just only aerospace engineers, right? I need to work with everyone because they're going to challenge me. They're going to help me think better. So this was with the White House and all of our university partners, and to put up best practices so that we could all learn from one another, a huge conference that we ran. Now, when it gets to the disruptive side, okay, how do we change things? How do we do things differently? Let's not just do it how we're always doing. So my example, I talked about Juno, and you saw this picture, but this is citizen science. Now we're saying, hey, world, come with us. Open up the data, open source data, open courseware, things like that, to say, tell us what you think. In the bottom right, those images of Jupiter, they're taken from something called the Juno Cam. It is a camera on the Juno mission that people, the public, anywhere in the world, You get to point it. Where do you want us to take pictures of? The red spot, okay, the storms on Jupiter. Take those images, you just go on the web so that the public can really, literally be part of the mission. And you know what? They're helping us discover those tens of thousands of new galaxies. So very exciting, I think. And then public-private partnerships. When I was there, I called it the new NASA. I was in charge of all partnerships. That was 800 partnerships with 120 nations. And just to show you how important this is, the government now, NASA is not doing everything itself, it's buying services. So I've highlighted here for cargo, resupply cargo to the International Space Station from SpaceX and Orbital ATK. And then the Russian partners as well, for both the astronaut supply and the cargo supply. And the bottom right, that's the Japanese supply. So again, opening it up, working with folks. Next, Boeing and SpaceX, 2018 to 2019, they'll be taking US astronauts, delivering them to the space station. So really thinking about public-private partnerships in a very different way, much more of a 50-50. Then we get to what about the technology? And so much is going on, and these investments hope continue and need to go on. First and foremost, flight. We will be flying on a plane like this, I venture to say, within the decade. I sure hope so. So we got back, it had been decades until we could invest in X-planes, experimental aircraft. Again, the government could make the investments in these. These will definitely be commercialized. This is the highest return on investments you can have to really help the economy. The top one is a supersonic airplane. Wouldn't you love to, get to Europe in half the time? I would. And in the middle, those are two ultra-efficient aircraft under development. 50% fuel reduction and 50% noise reduction. And then on the bottom is a hybrid electric aircraft with 12 electric, 14 actually, this one, 12 to 14, 7 on each wing, electric motors on the wings. So making these investments, again, as the government should do in the future of flight, in aeronautics here, so that it can be commercialized and the commercial companies can take it as soon as it gets to fruition where they can really realize them. Another example I want to show you that the technology investments, revolutionary innovation, is the James Webb Space Telescope. It's going to be 100 times more powerful than the Hubble. Can you imagine that? I can't even imagine that. We really don't know what we'll even be able to discover with James Webb. Hubble has been going for 26 years. It's an optical telescope. The James Webb is in the infrared. It'll be very complementary and really, again, looking to search for the beginnings. And this will really, hopefully, explain dark energy and dark matter. It's very unsatisfactory that we don't know what 96% of the material is in the universe. So we're on it. It'll really be revolutionary. It launches in 2018. Show you a little bit about our research and the technology of, you've seen spacesuited folks, but probably never thought of maybe an astronaut looking like someone in a leotard. But Paul Webb thought about this in the 70s, and I actually thought it was a great idea just well before its time, because he didn't have the materials to think about it. So if you're gonna be in a spacesuit, an extravehicular activity suit, right now it's a big gas pressurized suit. It's very massive. The current one's about 140 kilos, right? We're in microgravity right now with it, but that's about 300 pounds. That's not gonna work for the moon or Mars. So we said we have to design something very differently. Now the reason that this didn't go any further in the 1970s is coming right up here. You need to be able to dress yourself. Don't get to take your two friends with you to Mars. So good investment, but the soundtrack on this, or the NASA folks saying, wait a minute, it looks like a leotard for a 2-year-old. And you had to kind of squeeze yourself into it. So that really kind of spurred some of our work, and you'll see it. This is But this was 1970s, right? They didn't have the materials and the design capabilities that we have today. So again, I said, man, I think it was a really great idea, but just maybe well before its time. So we picked that up actually a while ago now. It's been about 15 so years. And behind the scenes is, again, this infographic. Today, human history across all the extravehicular activities, we've done over 500 in the world, humanity. The first mission to Mars, we're gonna stay there for about 600 days looking for the evidence of life, if we haven't found it before. It's about 1,000 spacewalks. So the first mission, this red bar. They had to change the scales. So it's a huge challenge. I think we need different capability. So show you just a little bit of some of the highlights of what we've been studying in the research. So it really is a second skin. We're trying to map and provide the pressure layer, the pressure. We need 1/3 of an atmosphere, that's 30 kilopascals, directly to your body. So we measure it, we model it. Here's an example of looking at the skin strains. And for an aerospace engineer, boy, oh boy, I never thought I'd know so much about skin and what the strains and stresses are. And it's a marvelous organ, I'll tell you that much, after studying it. And so we're really modeling it and saying, okay, can we literally shrink wrap some? What are the materials? This is the design patterning, because we want to give you full motion of mock-ups and prototypes. And an image here of Professor Anderson here in the biosuit with the helmet with a full kind of enhanced vision information helmet, if you will. Imagine you're the Mars Explorer. What's the day in life of the Mars Explorer? Well, I need to know the terrain, the slope. Can I go this way? What about my rovers and the vehicles that I'm with? How am I going to explore? So all of that's embedded kind of in the smarts of the helmet with this very mobile, lightweight suit that you get to explore. Because you're not going there to sit around. You're going there to find the evidence of life. So just kind of a summary on that. Really do envision where maybe human, version 2.0. It's really a hybrid human. You have the technology. It's really the materials and some of the patterning that we've been able to get very mobile, very lightweight systems. There's some mathematics, actually it's 3-dimensional eigenvectors for all the engineers down here. But you can imagine as you move, and if I want to give you maximum mobility, imagine you draw circles all over your skin, which a lot of my grad students have done, right? You have circles and you move, well, that circle will turn into an ellipse. And that's what you see in this little animation, those 2 red lines there that are just pivoting. If you trace that around the body, that's where you see a lot of this patterning come from. We call those lines of 9 extensions. So it's kind of like an internal skeleton, if you will. We want to give you maximum mobility, but also we have to pressurize you. So again, patterning and materials is kind of what's come out of this. And now we're applying active materials to basically put it on and take it off. As you saw in the video from the password, you have to be able to put it on and take it off. So that's just a little highlight of some of the technologies and research that we've been looked at. And again, getting to the 4th piece of, it even gets harder. What if you have to have the new breakthrough technologies and completely change your organization or look at a completely new business model to really transform, to be, do things in a very new way? And so I would argue that that's what happens when you go searching for exoplanets. There was a great talk already this morning. And we haven't really seen the exoplanets, but guess what? There's 6,000 of them to date. So 12,000 of them, NASA put up 1,200 of them. There's 6,000 so far. 1,200 are put up in a catalog. But it's about 24, a couple dozen that we're really interested in. They're in the Goldilocks zone. What does that mean? Well, they're not too hot, they're not too cold. They definitely could be habitable. Okay, one problem. They're 10 to 40 or more light years away. So you're not going to go there with humans anytime soon, right? But these great JPL artists said, well, what would they look like? So every star that you see in the night sky, now we actually think it's probably a planetary system. So much for learning 9 planets. Okay, thousands and thousands of these exoplanets, and huge news. This was the panel the session was on, the TRAPPIST-1. Did you hear about TRAPPIST-1? These are the latest exoplanets. Again, they're still pretty darn far out there, tens of light years away, but the phenomenal. So we're looking for Earth-like planets, again, that could potentially be habitable. So it's incredible, again, to think about just the breakthroughs and the knowledge coming back to us every single day. And we have to keep exploring. Another one that I really think is, kind of blows your mind, the ocean worlds. Earth being the most important, in my opinion, spaceship Earth. This is actually to scale. This is where we'll go to kind of some of our nearest neighbors to look for life, again, because they have oceans. And when you look for life, we say follow the water. Follow the water. So Europa is a great candidate. It'll be a Clipper mission. What does that mean? It means an orbiter to go look at a moon of Jupiter, Europa, because we think it has, we know it has an ocean underneath a lot of ice. And they're all up here. Enceladus is talking to us already. Vapor is spewing out of Enceladus. So we need to know what that chemistry is. Could there be life in all of these oceans? And again, bringing it back to our oceans, which we need to explore much, much more and learn about all the different life forms in our own oceans. So to kind of go full, so how will we do that? How will we do that? I believe that it'll be through global, international cooperation and exploration, and we really do have all of the world thinking about this and thinking about how we can all work together. And then kind of coming back closer to home, as I said, I do call, after Buckminster Fuller, I call Earth Spaceship Earth. I hope you like this view of it. It's from the Discover mission. Here's Earth, here's the sun. And this is really a space weather buoy, if you will, the Discover mission. It's hanging out at what we call the Lagrangian point, L1. It's gravity neutral. So that spacecraft is hanging out there taking pictures of that solar wind, that solar radiation that I showed in my movie, and it's saying, hey, Earth, in a million miles, here's what's coming your way. 1.6 million kilometers away. Big space weather buoy for us out there. And you get to see the moon orbiting like this each month. Amazing, amazing new images. There are 19 Earth-observing satellites up right now. Sea temperature, sea rise, soil moisture mapping, looking at the Earth from the orbital view with all of these assets. Space stations up there, all of the 19 Earth-observing satellites to give us critical information about Earth and life here on Earth. I'd like to put kind of this perspective for you to look at. Because if you take Earth and you shrink it down to the size of a basketball, our life support system, what separates us from everything else we know, our life support system, our atmosphere, that green glow you see right there, is 3 human hairs thick. At the scale of Earth as a basketball, that's our life support system. That's how fragile it is. That's how precious it is. That's how marvelous it is and incredible. So I think about that a lot in all of our exploring and in all of our work. Here's a recent image, and I got a chance to fly over Antarctica in the top left. Why are we flying over Antarctica? Again, to take the data. We have a satellite called IceSat, but we're waiting for IceSat 2 to be launched, so we fly over with an aircraft because it goes to Greenland in the summers and then Western Antarctica now in their summer. We're there in November, December, January to measure the glacial flows and melts, both the land ice as well as the sea ice. Because it's melting very rapidly. And down to the South Pole on the right, that's the Ross Glacier. I think it's very artistic, but it's also very scientific. This is where science and art meet for me. They're so incredible, these incredibly beautiful images. But again, then as scientists, we're taking all the data and seeing how they're changing. So I'd like to show you world temperature. This is actually 140 years of recorded temperature. What you're going to see is a change from the average. So 0, this is in centigrade, so it's 0 is the average. Yellow and orange go up to +2 centigrades. If you think in Fahrenheit, that's +4 or minus. The blue then goes down to -2 centigrade or -4. So you can raise your hand the year you're born. It's audience participation time. So here's 140 years of climate data from the average and hotter and colder. All right, thank you for participating. We have some audience folks out there. All right, some more hands going up. This is the students. Okay, so this goes through 2008. So 2014 was the hottest year ever recorded. Only surpassed by 2015, the hottest year ever recorded. We have the data in from 2016, the hottest year ever recorded. Matter of fact, the last 12 of 13 months have broken all records in terms of the temperature. So again, it's about Spaceship Earth. I want to then kind of end my talk on messaging, and I've spent my whole career dedicated to STEM, science, technology, engineering, and math, but I actually changed the message. For me, it's STEAMed, and this is a great, great conference to be at, because again, I'm trying to get people to Mars. Well, guess what, artists and historians and journalists, you paint the pictures. You write the words. You tell the history. That's the only way I know how to get people there, so I need to work with all of you. And for the little girl who's out there wants to be an artist, Grace, what? Grace, that's fantastic. I need you. And designers, there's 3D makers. There's a whole new generation of 3D makers. Guess what? We need them. So I actually call it changing the conversation. As an engineer, that sophomore course of mechanics where they weed everyone out, and then only the proud and the few get to remain, and everyone else gets to find other majors. No, we got it wrong. It's on us. Anyone who wants to do any of these disciplines, guess what? It's up to us to teach them and say, yes, you'll succeed. So we need to start filtering everybody in, is my message. Change the conversation, say it's for everybody. Thank you. Glad it resonates with you because you don't have to be the best in calculus and physics. I sure wasn't, right? They're tools. But you want to go to Mars? Great. Use these tools, right? So I think we really have to have that conversation and tell people it is for you. They have to see themselves in all this diversity of fields, and you know what? That's not even good. They have to belong. We need to create environments, again, to filter people in, to make sure that they see themselves and that they belong, and then surely we're going to have a huge impact and help the U.S. in this important field. So I'm going to end then with a tribute to the artists. A lot of them are here at the conference with us because, again, the artists, they've always been with us as scientists and engineers in all of our work. And so where science and art, design, and engineering all meet for me, this is scientific data. Anyone want to guess where it's from? This is kind of a hard one. But it's just, you can just look at it for its beauty as well, right? It's over China, called the fluvial fans, from a Landsat image. This one's closer to home. Some people might recognize Desolation Canyon and the Green River up top. Again, it's just spectacular, beautiful. I love these images. And it actually is a book called Earth as Art, and all this scientific data. Okay, this one I need help with, right? Anyone from, where's this? This is the orbital view. Anyone from South America? Yeah, these are the Nazca lines in Peru. That's what you see from orbit. That's what you see, ancient history and civilizations and humanity here, again, our mark, if you will, on spaceship Earth. But I think it's just beautiful as well, incredibly beautiful. Moving a little bit more contemporary, Andy Warhol. He painted with many, many other artists. Of course, what's the pictures of our exploration of the moon during Apollo? And most recently, Annie Leibovitz took this incredible photograph. And Annie was kind enough to donate this to the African American Museum, the new museum in Washington, D.C. And I sure hope you've seen Hidden Figures. It's amazing. Read the book, see the movie. It's celebrating all the folks that her history hasn't been written yet, but it's starting to be written. And again, shout out to all the women and men that actually helped NASA, and get to Apollo. And so next step for me is working with everyone and boots on Mars. And that's the end of my comments. I'm very happy to see you all today. Thank you.